Class 11th Chemistry. We were discussing Unit 2 Structure of Atom, and in this video we will discuss about electronic configuration of atoms and ions and stability of completely filled and half-filled subshells. First, what is the meaning of electronic configuration of atoms? The distribution of electrons into orbitals of an atom is called its electronic configuration. Electronic configuration of different atoms can be represented in two ways. For example, first way is SPD notation and second way is orbital diagram. Let us see one by one. First of all, SPD notation. In this, the subshell is represented by the respective letter symbol, and the number of electrons present in the subshell is depicted as the superscript like A, B, C, etc. The similar subshell represented for different shells is differentiated by writing the principal quantum number before the respective subshell. For example, nitrogen, atomic number is 7. Its electronic configuration is written as 1s2, 2s2, 2p3. These subshells are filled as per of above principle. That is, lower subshell filled first one. Okay. This 1 and this 2 and this 2 represent the principal quantum number. This S and this P represent the subshell. And these numbers which are in superscript of these subshells represent the number of electrons present in these subshells. Is it clear? Another way to represent the electronic configuration is orbital diagram. Now, in this representation, each orbital of the subshell is represented by a box and the electron is represented by an arrow. This is upward arrow, that is a positive spin, or an downward arrow as a negative spin. The advantage of this notation over the first one, that is SPD notation, is that it represents all the 4 quantum numbers. Again, take the example of nitrogen. Now we can say in one S subshell 2 electrons are there. That's why these 2 electrons are represented by these arrow with opposite spins in a box. In the same way, 2s subshell has 2 electrons with opposite spins and these are represented in the box. 2p subshell has 3 electrons, and as we know, p subshell has 3 orbitals. These boxes represent the orbitals, and each orbital occupy 1 electron as per the Hund's rule of maximum multiplicity. Is it clear? With same spin. This is called orbital diagram. Now we will discuss the electronic configuration of some of the elements. This is a table. In this, first contain element, then its symbol, then atomic number, and then electronic configuration. Hydrogen H, atomic number is 1, this is 1s1. Helium He, atomic number 2, this is 1s2. Lithium Li, atomic number 3. Now we can say in the first shell there is a 1 subshell, and first shell contain 1 subshell, and that subshell contain 1 orbital, that is 1s, and maximum number of electrons in s orbital is 2. When this is filled, next electron will go into the next subshell, that is 2s1. In the same way, beryllium Be, atomic number is 4, this is 1s2, 2s2. Boron B, atomic number is 5, 1s2, 2s2. Now this s subshell is filled as per its capacity. That's why next electron will go into the p subshell of the second cell. Okay, that's why this is 2p1. And as we know, in case of p subshell, maximum number of electrons occupied is 6. That's why from carbon, atomic number is 6. Number of electrons in the p subshell of the second cell is increases. 1s2, 2s2, 2p2. nitrogen N7, 1s2, 2s2, 2p3, oxygen O, atomic number is 8, 1s2, 2s2, 2p4, fluorine F, atomic number is 9, 1s2, 2s2, 2p5, neon Ne, atomic number is 10, 1s2, 2s2, 2p6. Now, in case of second cell, maximum 8 electrons can occupy according to the formula 2n square. Clear? And these 8 electrons will be distributed in S and P subcells. In S subcells, 2 electrons are there. In P subcells, 6 electrons are there. Now we can say this is second cell is completely filled. Now for the next electron, that is for sodium. Atomic number is 11, symbol is Na. Next electron will go into the third cell, that is 3s1. 1s2, 2s2, 2p6, this is 3s1. Now we can say this configuration is resemble with the neon. Okay, and that's why this electronic configuration can also be written like this. This Ne3s1. The electrons in the completely filled subcells are known as core electrons, and these core electrons can be written like this. Okay, and electrons in the electronic cell with the highest principal quantum number are called valency electrons. In a simple way, we can say number of electrons in the last shell is known as valency electrons. Okay. Then come to the next element, magnesium, Mg, this is 12, 1s2, 2s2, 2p6, 3s2, aluminium, Al, atomic number is 13, 1s2, 2s2, 2p6, 3s2, as subcell is filled. Then next electron will go into the P subcell of third shell, that is 3p1. Silicon, Si, 14, 1s2, 2s2, 2p6, 3s2, 3p2, phosphorus, P, atomic number is 15, 1s2, 2s2, 2p6, 3s2, 3p3, sulfur S, 16, 1s2, 2s2, 2p6, 3s2, 3p4, chlorine Cl, 17, 1s2, 2s2, 2p6, 3s2, 3p5, argon Ar, 18, 1s2, 2s2, 2p6, 3s2, 3p6. Okay. Now again we can say next electron. Now in which subcell next electron will go? As we have studied that in third shell there is 3d subcell is present. Okay, and after this third cell, next cell will start 4, and in the fourth cell electron will enter in the 4s. Now if we compare the n plus l value of these two, then we can say for this 3d, n plus l is 3 plus 2, that is equal to 5. Okay, and for 4s, this is 4 plus 0, this is equal to 4. Which one is less? That is 4s subcell has smaller value of n plus l. That's why after 3p, electron will enter 4s, not in 3d. Okay, that's why electronic configuration of potassium, atomic number 19, 1s2, 2s2, 2p6, 3s2, 3p6, and that is this 4s1. And up to this electronic configuration, this is similar to the argon. That's why we can also write like this is Ar4s1. Calcium, Ca, atomic number 20, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, or argon 4s2. Now this is as subcell of the fourth cell is filled. Now next electron will go into the 3d. Okay, that's why we can say that it's scandium. Atomic number is 21. This is 1s2, 2s2, 2p6, 3s2, 3p6. Then next electron will go into the d subcell, 3d1, and this is 4s2. Titanium, 22. This is 3d2. Vanadium, 23. 1s2, 2s2, 2p6, 3s2, 3p6, 3d3. Okay, then come to this chromium. Atomic number is 24. As per the rule, if we write the electronic configuration, it should be 3d4 and this is 4s2. But this is exception. Okay, and why this is exception? One electron will shift to this, and this become 3d54s1. Okay, actually this is due to the extra stability of the half filled subshell. Okay, in this way we can see this is 3d5 is half filled, and this is 4s1 is also half filled. That's why we can say this is extra stable. Okay, then manganese 25, this is 3d5 4s2. Iron 26, this is again now 3d6 4s2. Cobalt 27, now again see symbol of cobalt, C capital, O is small. Don't write both capital, otherwise it will be carbon monoxide. This is 3d7. Nickel Ni28, this is 3d8. Then again come to this copper, atomic number is 29. Okay, if we write as per the rule, then its electronic configuration should be 3d9 4s2. Clear? But actual electronic configuration of copper is 3d10 4s1, and its again reason is this is fully filled subshell, and half filled subshells have extra stability. Okay, that's why you have to remember the electronic configuration of chromium with atomic number 24 and electronic configuration of copper with atomic number 29. These are the exception case, and this exception is due to extra stability of half filled and full filled electronic configuration. Okay, and then last come to the zinc, atomic number is 30. This is again 3d10 4s2. Dear students, at least atomic number 30 up to atomic number 30 you have to remember the electronic configuration of elements. Clear? Now what the reason of stability of completely filled and half filled subshells? The completely filled and completely half filled subshells, sorry, this is completely filled and half filled, this is wrong. Completely filled and half filled subshells are stable due to the following reasons. First one is symmetrical distribution of electrons. It is well known that symmetry leads to stability. The completely filled or half filled subshells have symmetrical distribution of electrons in them and are therefore more stable. Another reason is exchange energy. The two or more electrons with the same spin are present in the degenerate orbitals of a subshell tend to exchange their positions, and the energy released due to this exchange is called exchange energy. The number of exchanges that can take place is maximum when the subshell is either half filled or completely filled. As a result, the exchange energy is maximum, and so is the stability. Now, what is the meaning of this exchange? We can see. Now, if we say this is the half filled electronic configuration. Okay, this is first electron. You can say now this electron can exchange its position with this one, or with this one, or with this one, or this one. We can say that this one electron can exchange its position with the 4 electrons. That's why it has the 4 exchanges. In the same way, this is the second electron. This can exchange its position with this one, and this one. That's why this electron has 3 exchanges. Okay. In the same way, this is the third electron. This can exchange with these 2 electrons. That's why it has the 2 exchanges. And in the same way, this is fourth electron. It can exchange its position with this one. 1 exchange. Why electron? 4. Now we can say if we count these exchanges in case of chromium, which has the 3d54s1, total exchanges in d orbitals are 10. That is, this one is 4, this is 3, this is 2, and this is 1. Total exchanges are 10. If we assume that its electronic configuration is 3d4 4s2, 3d4 4s2, then d electrons can exchange in 6 ways only. How? We can say that this electron can exchange with these 3. Okay, this is 3, and this electron can exchange with these 2. 3 plus 2, and this electron can exchange with this one. 3 plus 2 plus 1 is equal to 6. Hence, the number of exchanges is maximized when chromium has half filled d subshell. More the exchanges, more the stability. Clear? Now, students, we will discuss the electronic configuration of ions. Two type of ions are there, positive ion and negative ion. Positive ion is formed by the loss of electron, and negative ion is formed by the gain of electron. Okay. Now, like see, this is H minus. As we know, hydrogen atom electronic configuration is 1s1. H minus means one electron it gains. That's why its electronic configuration is 1s2. The same way, this is O2 minus, oxide ion. Electronic configuration of oxygen is 1s2, 2s2, 2p4. And this is 2 negative charge, means it accept the 2 electrons. And that's why this is 1s2, 2s2, 2p6. This is Na plus. It is formed from sodium. 1s2, 2s2, 2p6, 3s1. When this electron is loose, then it will acquire the one positive charge, and its electronic configuration becomes 1s2, 2s2, 2p6. Now you can compare the electronic configuration of these two species, O2 minus and Na plus. Same electronic configuration, or we can say same number of electrons. Okay, such type of species which have same number of electrons are known as isoelectronic species. Species have same number of electrons, like O2 minus and Na plus, both have 10 electrons. Okay. Now come to Cl minus, chloride ion. The electronic configuration of chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. One negative charge means one electron extra in 3p subshell. It becomes 3p6. Calcium ion. Electronic configuration of calcium is this. And from outermost shell, when 2 electrons are loose, then it becomes 1s2, 2s2, 2p6, 3s2, 3p6. Then again you can compare number of electrons in these two species. Both have 18, sorry, you can say that is yes, both have 18 electrons. That's why this is chloride ion and Ca2 plus ion. Both are isoelectronic with each other. Now come to the scandium. Scandium ion. Electronic configuration of scandium. If you compare last one, that is this is 3d14s2. There is a 3 positive charge. It means these electrons, there is 1 electron from 3d and 2 electron from 4s are loose, and this becomes 1s2, 2s2, 2p6, 3s2, 3p6. Then again come to this is chromium. Electronic configuration, if you compare last one, that is 3d54s1. Okay, when it lose 3 electrons, now be careful here. When it lose 3 electrons, first this electron is loosed. Okay, then remaining 2 electrons will go from this 3d, and this becomes 3d3. Okay, dear student, what mistake you will do when you write the electronic configuration of chromium? As you know, atomic number of chromium is 24. And when you are asked to write the electronic configuration of Cr3 plus, you assume that this is loose 3 electrons. That's why you can write it has the 21 electrons. And when you write its electronic configuration, then this becomes for 21 you will write 1s2, 2s2, this is 2p6, this is 3s2, this is 3p6. Okay, these are the 18 electrons. Then next one 4s2, these are the 20. And now next electron will go into the 3d, and this is 21. But this is a wrong. When you write the electronic configuration of ions, first write the electronic configuration of neutral atom like this. Okay, as per the rules. What if exception is there, follow that one. Then whatever the positive charge present on that ion, start the removing electron from outermost shell. In this case, outermost shell here. As we know, last electron, and when you write the electronic configuration, last electron enters in this is 3d. But when you write the electronic configuration of ion, first you remove the electron from outermost shell, which is 4s here. Is it clear? That's why I remove 1 electron from this 4s and 2 electrons from this is 3d. Then that's why its electronic configuration becomes 3d3. Okay? Don't write like this. Now come to the Fe2 plus. First write the electronic configuration of neutral Fe atom and its atomic number is 26. Okay, that's why this is 3d64s2. When this is a 2 positive charge, remove these 2 electrons. Don't remove the electron from 3d. Remove the electron from outermost shell, which is 4s. That's why its electronic configuration is 3d6. In the same way, copper. First write the electronic configuration of neutral copper atom. Its atomic number is 29. And as we have discussed, this is the exception case. This is 3d10 4s1 and we have to remove the 2 electron. That's why 1 electron you will remove from this 4s and 1 electron from this is 3d. That's why this its electronic configuration becomes 3d9. Is that clear? Be careful when you write the electronic configuration of ions. What is the utility of knowing the electronic configuration? The modern approach to the chemistry depends almost entirely on electronic distribution to understand and explain chemical behavior. For example, questions like why 2 or more atoms combine to form molecules? Why some elements are metals while others are non-metals? Why elements like helium and argon are not reactive, but elements like the halogens are reactive? Explanations of these type of questions are obtained from the electronic configuration. That's why you must know how to write the electronic configuration of the atoms and ions. Okay, student? Thank you.